Transition elements and coordination compounds. Remember that the transition metals are the atoms in the B groups. They are in the center of the periodic table shown here. They also have multiple oxidation states. The most stable oxidation numbers are shown in red. They are all metals, and actually quite beautiful in some cases, like copper. The properties of the transition elements are that they have partially filled d orbitals, they are all metals, they have high melting points and boiling points with the exception of group 2b, they have several oxidation states, and they form highly colored compounds. Often they are paramagnetic. They also form complex ions. In this case, copper 2+ attaches to 4 ammonias, forming the complex CuNH3 2+. This is a cationic complex. Here, iron 3+ attaches to 6 cyanide ions, forming FeCN6 3-, an anionic complex. The anionic complex can form a compound with potassium. Let's see how the charge on the complex changes. In the compound PtNH3 Cl2, the complex is inside the brackets PtNH3 and that carries a 2+ charge to balance out the chlorides. Here we have PtNH3 bringing a chlorine inside, and there's a chlorine outside of the complex. The complex is PtNH3 taken 3 times Cl+. Here platinum NH3, this time 2, and chlorine 2. This is a neutral complex. Here potassium attaches on the outside to the complex, forming the compound PtNH3 Cl3. The complex is anionic, PtNH3 Cl3-. K2PtCl4 is the compound. The complex in this case carries a 2- charge. It is anionic, PtCl4 2-. A coordination compound typically consists of a complex ion and a counter ion. In this example, we have cobalt in the center, and attached to it are 2 chlorines and 4 ammonias. A complex ion contains a central metal cation, in this case cobalt, bonded to one or more molecules or ions. The molecules or ions that surround the metal in a complex are called ligands. A ligand has at least one unshared pair of valence electrons. Water, ammonia, chloride ion, and carbon monoxide are examples of that. The atom in a ligand that is bound directly to the metal atom is called a donor atom. Water and ammonia fit this case. The number of donor atoms surrounding the central metal atom in a complex ion is called the coordination number. Ligands with one donor atom are referred to as monodentate. Water, ammonia, chloride are monodentate ligands. If the ligand has 2 donor atoms, it's referred to as bidentate. Ethylene diamine is an example of that. If there are 3 or more donor atoms, it is referred to as a polydentate ligand. And an example of that is EDTA, which stands for ethylene diamine tetraacetic acid. Here we have the structure of the bidentate ligand ethylene diamine. Notice the 2 amino groups at the end and the ethylene in the center. In the cobalt complex, there are 3 ethylene diamines attached. Why 3? There are 6 attachment sites, and each ethylene diamine can attach to 2. In the polydentate ligand EDTA, the entire metal atom, in this case lead, is surrounded by the EDTA. EDTA is actually a therapeutic treatment for lead poisoning. It surrounds the lead in the bloodstream and can be extracted. Bidentate and polydentate ligands are called chelating agents. This table shows some common ligands. You should study them and their structures. What are the oxidation numbers of the metals in potassium gold hydroxide and chromium ammonia nitrate? Let's take the first one, potassium gold hydroxide. Remember that the hydroxide has a -1 charge. That potassium has a +1 charge. So the complex, because the potassium is on the outside, is -1, and the hydroxide is 4-. What balances that out? Gold 3+. In the second example, nitrate outside of the complex has a -1 charge, which means that the complex must be +3. Ammonia, of course, has no charge, so where does the +3 charge come from? The chromium ion.